All right, hello everybody. Hope you're all doing well. Welcome back to, I guess this is now week 4 of online lessons. We've just about made it through a month, which is pretty crazy. Anyway, so today we're going to hop into our next lesson in physics. And this is a really important one. This one, we're talking about what we call vector measurements, which are a lot different than the scalar measurements we've been using so far. Basically, the difference between them complicates our math a little bit because what happens is we start talking about direction when it comes to a vector measurement, right? So in physics, we have two types of measurements or two types of quantities that we look at. The first are called scalar quantities, and this is what we've kind of been looking at so far. Scalar quantities always tell us magnitude, like how much something is, but they do not give us a direction. Nothing we have talked about so far has included direction, or if it has, it's been unnecessary. It doesn't help us at all, and we don't use it. Like if I said, like, oh, this guy goes 20 meters north, that didn't change how we approach the problem compared to if they went 20 meters south. Okay. But vector units, what they do is they give us the amount, the magnitude, and they give us a direction. Okay. So scalar measurements are things that we've basically been talking about so far. Things like speed, distance. A couple of other ones are things like mass. All right, because mass can't have a direction. Time is also a scalar measurement because time can't have a direction. All right, but basically, if it can have a direction or we attach it to it, that makes it a vector measurement. Okay, so the scalar measurements you need to know are speed and distance, mass, and time. Vector measurements, they'll tell us how much something is and what direction. So what we do is we actually have different measurements that we use for vectors that are similar to our scalar measurements, but a little bit different. So instead of speed, when we have a vector or in a vector form, we call it velocity. Instead of distance, with vectors, we talk about either displacement or position. All right. And what they do when I say, if you're not sure what I mean by the magnitude, like a speed measurement would say like, oh, I'm going 4 kilometers per hour. If I was a vector measurement, if I was talking about velocity, I would say I'm going 4 kilometers per hour southeast. It's telling me how much, that 4, and it's telling me which direction. All right. The big distinction between vector and scalar units, one of the ways that we tell which one that we're using is because they use the same symbols, we draw an arrow over top of our vector measurements. So in scalar, when we have distance, we always use d to represent it. If it was a vector unit, we would also use a d for displacement, but we put a little arrow on it like that. All right. Same thing with speed. Speed is a v. All right. In vector measurements, velocity is also a v, and it's got that little arrow on it. Time should never have an arrow on it. It doesn't matter if I'm using a vector or scalar measurement because time can't possibly have direction. A couple of other vector measurements are acceleration, which we'll talk about, I think, next week, and force, which we'll talk about a few weeks from now. It's the subject of our third book. But let's get into how this affects us and how it changes our math. Okay, before we get into anything crazy mathematically, I want to talk about just the difference between distance and displacement, or sometimes called the position. It is the same thing. They just have slightly different meanings, but not enough to affect us, because they are related, but they are not the same thing. All right, so if I travel a certain distance, that might be different than my displacement. So I just want to make sure you guys understand the difference between these two things, which then leads us to the difference between speed and velocity. It's not just that I'm attaching a direction to it, because otherwise this would be really simple and I wouldn't have to do a whole lesson on it. So let's talk about distance here. Distance is, imagine somebody leaves their front door, okay, and they go and walk a certain number of kilometers here. So let's say they go this way. That's not what I wanted to draw. Try that again. You'd think I would understand how to use this thing by now. There we go. So let's say they go this way. All right, and they go that far. Perfect. Then they turn around and they head back this way. Let's say up to there. Okay, and that's where they stop. All right. So they started right here. Let's just draw. Let's say they started right here. Okay, right at the start of that arrow, and then this is where they ended up after all was said and done. Okay, the distance that they traveled is going to be how far they traveled this way plus how far they traveled that way. It's going to be, I always like to call the distance basically how far you walked or how far you drove. It doesn't matter what direction you went in. It would be this arrow plus this arrow. We could even assign numbers to this if we want, just to make it a bit easier to talk about. So if this person walked all the way this way, let's say that was 10 kilometers. And then they head back, let's say this is, I don't know, 6 kilometers. Okay? Their distance from this whole walk is going to be those two things added together. So in total, they walked 16 kilometers. Okay, I just added those two together. That makes sense. Displacement, the way you can think about displacement is that it is a measurement of how far you are now from where you started. So with displacement, we don't care that you did all this and then turn around and did all this. We care about where did you start, where are you now, and how far apart are those two things. So to figure out the displacement here, what we would do is essentially, and it's a little bit more complicated than this, but basically the idea is we're going to go 10 kilometers, because that's how far we went in the first part of our trip, minus 6 kilometers, because we went back. So in total, my displacement is going to be 4 kilometers, and because I care about direction here, we're going to say it went 4 kilometers east, okay? And the way we show direction in vector measurements is by writing the direction in square brackets next to the unit. This could be north, east, south, west. This could be up, down, left, right. Those are typically the measurements that we'll use. Okay, so the big difference here between distance and displacement, distance is how far did you walk. Displacement is how far are you from where you started. All right, it doesn't matter about the journey. It cares about just the destination. Okay, so then let's talk. I'm just going to clear this out of here so I have a little bit more room. There we go. So let's talk about then the difference between speed and velocity. We know that our formula for speed that we were using last week is v equals d over t. Okay, our formula for velocity is exactly the same with one slight difference, okay, which is that our velocity is equal to our displacement divided by time, okay? So mathematically what it does is it changes what we have to use. So in a case like this where somebody changes direction, like I did up here, if I asked you for the speed, you would use the total distance they traveled, 16 kilometers, divided by how long the trip took. Over here, we would use our displacement, how far are we from where we started, divided by time. So in this case, I would use that 4 kilometers that I had up on the screen here that I had calculated for displacement. I would go 4 kilometers divided by how long the trip took. Okay? So what velocity does is it basically assumes that you went straight from here to here, and it tells you how fast you did that, basically. So basically how long, or using the time it took, it goes this displacement divided by the total time. All right, so for the math around vectors, it doesn't sound so bad. It just means we change the fact that we're doing displacement divided by time rather than distance divided by time. But the problem that we have with vectors is that we have to mathematically be able to account for when something changes direction. All right, I can't just use numbers the way I would for scalar units because every time I did that, my distance and my displacement would end up being the same. So what we have to do when something changes direction is we need to assign values to the directions that have gone. So what we do in physics is we have kind of arbitrarily chosen certain directions to be positive and other directions to be negative. That way we can get an opposite. So when things travel in opposite directions, we now have a positive going one way and a negative going the other, and that helps us mathematically account for what we're doing. So the conventions that we use, and these are in your book and your notes if you haven't done it so far, is that number one, right is always positive, okay? So whenever we're heading to the right, we assume that that is a positive direction. When something is heading up, we also assume that that's positive, okay? When something heads downwards, we say that it's negative, going in the negative direction. And when it's heading to the left, we also say that it is negative. It kind of ends up looking just like a Cartesian plane like you would see in math class, but we've just assigned those directions that way. We can do the same thing with north, east, south, west. I'm just going to clear those guys out so I give myself a little bit more room. We do the same thing with north, east, south, and west. North ends up being positive. East ends up being positive. South is negative, and west is also negative. All right. What this does is when we start assigning positives and negatives to our values that we take from our problem, now we can find out which direction something was actually moving in or where it actually ended up based on our answer. So if I do a problem in with a vector and I get my final answer and I get a negative number, that tells me it was heading west or south or down or left, depending on what the problem gives me. So a problem we either say is heading north and south or east and then west or left and then right. It will tell you which sort of set of directions we're using. And then our answer, whether it ends up being positive or negative, tells us what direction it ended up or what direction it was traveling in. Right? So let's do a few examples. These are on page 9 of your booklet. All right, so our first problem here. First of all, I have my answer wrong in the answer key. I just noticed it when I was making this video, but we'll go through it. So it says Grace walks 35 meters north for 30 seconds, stops for 1 minute, and then travels 60 meters north in 60 seconds. And for this, it wants us to calculate the total distance, total displacement, average speed, average velocity. All right, so we're doing all 4 types of calculations. So let's see kind of what we get here. So what's happening here is it's giving us a trip in multiple parts and then asking us the total distance. To calculate total distance, all we do is add the distance she traveled in each part together. So I'm basically going like distance 1 plus distance 2. And if I had more distances, I would just keep adding them. Okay. So in the first part, she went 35 meters. The fact that she stopped doesn't really bother us here. Okay. So then in the second part, she went 60 meters. So in total, her distance is 90 meters, 95 meters. Wow. Nice job, Mr. Barry. Feeling good today. 95 meters. There we go. All right. So our total distance here is 95 meters. Then we go to total displacement. So same thing, except now we have to watch what direction she went. All right. So here she went 35 meters north. So we're going to use a positive 35. And then she continued 60 meters north. So we're going to continue to use positives. Okay. So again, I'm going to go 35 meters plus 60 meters. When I add those together, I get 95 meters. But but now I need to make sure I include the direction that it traveled in, which was north. Okay. I'm just going to clean this up a little bit. All right. Sorry, I tried to clean that up a little bit so I gave myself enough space. So that's great. And if you'll notice here, both of these are exactly the same. The only difference between them is that this guy has a direction on it, but otherwise we did the exact same work. All right. And the reason that they end up being the same is because she traveled in the same direction. She never turned around. She didn't come back. So when somebody just goes in one direction, their distance and displacement will be the same. All right. But now let's take a look at speed and velocity. For speed, we're going to use our v equals d over t formula. Okay. But before we can do that, we need to figure out the total time that she took. And this is where I screwed up in my answer key. And it's funny because I put this in here to mess with you guys, and I ended up messing with myself. Anyway, so total time, we got to look at the 3 different parts of the trip. Basically, how long did the trip take in total? Not just how long was she moving for, but for the whole trip, the time for the entire trip. So we have to add these 30 seconds plus 60 seconds, we know is 90 seconds, right? But then we also have to take into account this 1 minute that she stopped for. That's still part of the trip, okay? You can think of it like when you, I don't know, if you go on a long car ride to go on vacation or something like that. If you stop for lunch, like so as an example, I go out to Munster, Saskatchewan to see my in-laws, and it's an 8-hour drive, okay? Actually, it's a 7-hour drive, but I stop usually for lunch, which takes about an hour sometimes. And so it makes my trip about 8 hours, okay? It's still a part of the trip. It's still part of the journey. And so if I were to figure out the how fast I went on average over the course of the trip, the fact that I was stopped for a big part of that trip still makes its way into the trip time, okay? So what our total here for the time traveled is, I'm just going to write it up here just so we have it. I just don't want to take up space. It's going to be 30 seconds, okay, plus the 60 seconds that she stopped, plus the 60 seconds of the second part of the trip, okay? So in total, she went 150 seconds, or this trip took 150 seconds, okay? So that's the time we're going to be using when we do this formula. So for average speed here, we're going to go our distance our 95 meters divided by our total time, 150 seconds. And when I do that, when I put that in my calculator and then I put the right number of significant digits, my speed that she went was 0.63 meters per second. Okay? We're going to do the same calculation for average velocity now. So velocity, remember, is v equals d over t, except the difference is we have to use our little arrows to show that we're going to use direction. Okay? So for average velocity, we're going to go, our velocity is equal to our displacement of 95 meters. Okay? You notice I don't put the direction on here. The fact that it's a positive number is indicating the direction. We add the direction at the very end as a part of our final answer. Okay? So we're going to go 95 meters north, so positive, divided by, again, 150 seconds. And when I do that, I get 0.63 meters per second. I ended up with a positive answer. So I know that the direction she went in her velocity was north. Okay? So again, what we do, and this will make more sense when we get into the next problem, but what we do is we take the direction that we had, that we were given, we turn it into a positive or negative number, and then from there, we check to see if our answer is positive or negative. If it's positive, we put the positive direction at the end. If it's negative, we put the negative direction at the end. All right, so let's do another one. This one where somebody actually changes direction, because that makes things a little more complicated. It starts to make sense why we're using positives and negatives in this case here. Okay, so a person travels 26 kilometers west and then turns around and goes 19 kilometers east. The entire trip takes 40 minutes. It wants us to know the total distance and the total displacement. All right, so we'll do those two first. So total distance, again, we're going to go our first distance plus our second distance. Okay, and we're always adding. I just want to point that out because it's going to become important for us in the next part. So our first distance was 26 kilometers. I don't care what direction because I'm asking for distance. My second distance was 19 kilometers. Again, I don't care about direction. And when I add those two things together, I get 45 kilometers. Okay, so this person covered 45 kilometers over the course of their entire trip. But let's now go into displacement. Displacement is also distance or displacement 1 plus displacement 2. Notice again, I'm still adding. Okay, the problem is one of these numbers is positive and one is negative. Okay, so the fact that this person went 26 kilometers west, remember that's a negative direction. Okay, 19 kilometers east, that's a positive direction. So what I'm going to do mathematically is I'm going to go, okay, and I would use brackets, you don't have to, is negative 26 kilometers. Okay, I turned that direction into a positive or negative, okay, plus 19 kilometers, okay, and this one is positive because east is positive. So I have the fact that it is negative tells me it's heading west. The fact that this is positive tells me it's heading east. These directions could be changed to down and then up. This could be left and then right. It doesn't matter. It tells me what frame of reference to use here. So when I go negative 26 plus 19, what I get as an answer is negative 7 kilometers. I can't just leave it as negative 7, okay, because negative 7 kilometers doesn't really mean anything. It sounds weird. So what we do is we turn it into its real world application. So negative 7 kilometers means that I went 7 kilometers and then I put my direction in. I put down what that means. So this person ended up 7 kilometers west of where they'd started. Okay, that's how it's displacement. So now we'll do the speed and velocity calculations. All right, so we're going to use our v equals d over t. And this time, because I don't know why I always do this to you guys, it gave us the time as 40 minutes. We know we have to turn that into hours, right? Because we either have speed in kilometers per hour or meters per second. Because this is already in kilometers, we want to just convert this into minutes, or into hours, sorry. So you can easily do that in your calculator. You go 40, oh my goodness, I'm running low on room. We can go, let me just zoom out a little bit here. So we can go 40 minutes times 1 hour over 60 minutes. Basically going 40 times 1 divided by 60. When I do that, my time effectively becomes 0.67 hours. Okay, I'm just going to zoom back in. There we go. Okay, so 0.67 hours is our time. So when we put this into our calculator here, we're going to go our velocity is distance divided by time. Our total distance that we've calculated before was 45 kilometers. So our speed is going to be 45 kilometers divided by our total time is 0.67 hours. And when I throw that in the calculator, what I get as an answer is 68 kilometers per hour. Okay. Average velocity, and I can't quite see it. There it goes. So average velocity, now we have to use our displacement. Okay, we're not going to use this number here. We have to use displacement with this one. So we're going to go our velocity is equal to, remember our total displacement is 7 kilometers west, which is -7. When we're doing math, we have to put that back into a negative or positive. So we're going to go -7 kilometers divided by still the same time, because time doesn't change. It took this person 40 minutes to go that -7 kilometers. Okay. And when I do that division, I get negative 10.5 kilometers per hour. Okay. And you'll notice here, because I did addition over here, I ended up with one significant digit on this. So I have to round this to be one significant digit. So when I do that, I'm going to get -1 times 10 to the power of 1 kilometer per hour. And because I have to turn that negative into a direction, I'm going to say 1 times 10 to the power of 1, seems silly to say that, kilometers per hour. And I ended up with a negative, so I know that my direction here is a west. Okay, so that's what happens when somebody changes direction. That's why we have to use that negative and positive, so we know where they ended up. All right, guys, last example, and I will tell you that this one is a mean question. I hate it, all right? I don't know if that's why I put myself in it. I don't know. But this question is asking us to do a lot. So this one's going to take a little bit more work, but nothing that we can't already do. Nothing we haven't seen before. It just is asking quite a bit of us, all right? So this one is saying Mr. Barry walks with a velocity of 2.3 meters per second north for 3 minutes. Then he turns around and runs at a speed of 8.1 meters per second. That should say south. Let me just quickly write that in there. I just missed it. It is in your book. Okay. So it had south for that second part for 2 minutes. All right. And then as usual, it wants us to the total distance, the total displacement, and then we'll do speed and velocity on the next slide. Okay. Because I need a lot more room here. The reason I say that this one is tricky is there's two things going on. One, it's not telling me distance that I traveled each step. It's telling me how fast I was going, which means that for the distance and displacement calculation, I'm going to need to do a bit more math first to figure out how far I went at each stage. What I mean by that is we're going to have to use our V equals D over T formula, but we have to use the rearranged version to find distance, okay, or displacement, I guess. And so we're actually going to, if you remember from Monday's video last week, the rearranged version of that, looking for distance is equal to velocity times time, or speed times time, I should say. Okay, so this is the formula we're going to need to use to figure out how far he went here, and then how far he went here. All right, so our distance for this first one, basically we're trying to find distance number 1. We're going to use D equals V times T. Okay. Our speed for this first part was 2.3 meters per second. Our time is 3 minutes. See, this is what I mean. This is a tough question, just because I have to do a lot of conversions. 3 minutes. I'm just going to do this quickly. I hope you guys can figure out 3 minutes would be equal to 180 seconds. 2 minutes would be 120 seconds. All right. If you're not sure how I got that, please just ask me in our conversation on Tuesday. All right. So we're going to go 2.3 meters per second times 180 seconds. When I do that, my first distance that I traveled is going to end up being 414 meters. All right. Now for distance number 2, for the second part of our trip. Okay. You can almost read that too. There we go. Same thing. This time we're going to go, again, speed times time. This time our speed was 8.1 meters per second. Our time was 120 seconds. Okay, and when I multiply those together, I get 972 meters. Okay, I'm just going to zoom out a little bit to give myself a bit more space here. So we have 972 meters in that second step. So our total is just going to be adding those two together. So I'm going to go 414 meters plus 972 meters, which ends up equaling 1,386 meters. And if this was the total problem, this is all I was asking, you would need to use the right number of significant digits to figure that out. You look back at the original numbers, these guys here. These ones both have 2 significant digits, so this needs to have 2. So I'm going to round this to 1.4 times 10 to the power of 3 meters. All right, now let's head over to displacement. All right, just change the zoom a little bit just so we can see it a little bit better. So we're going to do the same thing, but now we care about what direction, right? We have to use positives and negatives for our directions to make sure that we have the correct thing. But we are going to do the same formula. We're just using d equals v times t. This time d is displacement, v is velocity, right? So our first one, for the first part of the trip, we're going to use velocity times time. The first one was heading north, so we're going to use that as a positive number. So we're going to go 2.3 meters per second times 180 seconds. And because I'm so good at math, I'm not even going to put this in my calculator. I happen to know just off the top of my head that the answer is 414 meters north. Okay. Same thing for distance number 2, or displacement number 2. I always do that. Okay. This time we're going to go, the fact that I was running south means that I need to have this 8.1 meters per second as a negative. Okay, that way it mathematically accounts for the fact that I changed direction. So I'm going to go negative 8.1 meters per second times 120 seconds. Ooh. And because I'm so good at math, I just happen to know off the top of my head that that's negative 972 meters, okay, which is the same as 972 meters south. Ooh, geez. I'm running low on room. So again, we're going to do the total, but now I'm still adding them, as always, except I'm adding a negative. All right, so when I put these together, for the total, I'm going to go, let's go write dt, as in like total. I'm going to go 414 meters, that's a positive number, because there's a positive direction, plus negative 972 meters for my second distance. Okay? When I add those together, basically subtracting them, I end up with a total distance of negative 558 meters, which if I use the right significant digits, which should be 2, just like our first example, I should end up with 5.6 times 10 to the power of 2 meters south. Okay, so what happens here is because my answer ended up being negative, that means I ended up in the south direction. It means I ended up in the negative direction. All I'm doing is taking this negative and turning it into that. Over here, I don't care about that at all. All right, so that's our distance and displacement. Try and remember, because I'm going to switch the slide here, try and remember these two numbers. If you forget, just rewind, okay? I have them on my piece of paper in front of me. We're going to need them for the next part of this. All right, so it's still the same problem, except now it's asking us for speed and velocity. And I just wrote down the distance and displacement that I calculated on the last slide. One thing I want you to notice is that I'm using the unrounded version. You never want to use your rounded version in a calculation. All right, as a final answer, that's what you want to put down. But if you have to do more math with it, go back to the unrounded number, which is why I'm not using that 1.4 or that 5.6. I want to make sure I'm using the unrounded versions of these. Okay? This last part is actually easy. We've already done all the grunt work, all the hard work in this. So now we just need to find average speed and average velocity for the entire trip. Typically, when you think of an average, you go, oh, you take the two speeds, add them together, then divide by 2. But the problem is that he's running an unequal amount for both of them. If he was running 2 minutes this way and then 2 minutes this way, you could actually do that. But because he's running for unequal amounts of time, we have to calculate the average speed by going total distance divided by total time, or total displacement divided by total time. That's why we have to do these first kind of set of calculations. Anyway, so our calculation for speed is still v equals d over t. Okay, our total distance is 1386 meters. Our total time is, remember, we went 180 seconds here. Sorry, this is 180 seconds. I should write that on here just so you guys know where I'm getting the numbers from. So that's the same as 180 seconds. This over here is the same as 120 seconds. So my total is going 120 plus 180. So my total time here is 300 seconds. Okay, just adding those two times together. When I do my division, what I get as a final speed is 4.6 meters per second. Okay. Over on the other side, we're going to do the same calculation, except we're going to use our velocity is equal to displacement divided by time. Okay. So we're going to use our negative 558 meters that we calculated on the last slide. Okay. And still divide by our total time. Time never has a positive or negative. Time is always positive, right? It can never go backwards. So our time is still 300 seconds. And when I do that division, what I get as a final answer is negative 1.9 meters per second. I have to turn that negative back into a direction. So what I get is 1.9 meters per second, and negative in this case was going to the south. Okay. I hope I didn't mess you guys up by doing those. Oh, geez. I hope I didn't mess you up by doing those time conversions and then just adding them together. Let me know if you are confused on how I did these. But this is what we get as a final answer. If you're ever concerned about significant digits and you're not sure how I got to two significant digits here, the best thing you can do is always just go back to the original problem, look to see how many significant digits are there, and then just round to that many significant digits. So these guys all have two significant digits, so my answers all have two significant digits. All right, so that's the end of the lesson on vectors. Please make sure you take some time to go to the PowerPoint and record the blanks on the previous couple of pages. Hopefully you got these examples down. They're on page 9. I guess I didn't say that at the beginning. Anyway, the point is, what I'd like you guys to do is page 10 and 11 for practice. It really helps you figure out the difference between distance and displacement and when to use positives and when to use negatives. All right, we're going to continue with vectors on Wednesday, talking about how we graph them. So the better your understanding of them quantitatively right now, the better. Page 10 and 11 don't have a ton of questions. They shouldn't take you too long to do. The boot camps, though, I will put the boot camp up on vectors, and I really strongly recommend doing that boot camp. Normally I'm like, yeah, you can do it as practice, but this one I would say is better practice than what's in the booklet. And it's a very key thing because we're going to keep talking about positives and negatives as we go, and you need to make sure you have a good handle on when to use negatives and why we use negatives. Anyway, hope you guys have a great day. Hope you're all safe. Hope you and your family are good. We'll see you guys online.